Look up at the night sky, and what do you see? A serene, unchanging sea of stars. Think again. Hidden within that vast darkness lies a cosmic drama of unimaginable scale, a never-ending cycle of destruction and rebirth that shapes everything around us. Galaxies collide in violent embraces, stars explode with the fury of a trillion suns, and from the ashes of these cataclysms, new worlds are born. This isn't science fiction. This is the heartbeat of our universe, a rhythm older than time itself. And today, we're going to witness it together. What if I told you that the very atoms in your body were forged in the heart of dying stars? That the gold in your jewelry, the iron in your blood, were once scattered across the cosmos in the aftermath of stellar explosions? This is the magic of galactic rebirth, a process where endings are just beginnings in disguise. Across billions of years, the universe has perfected the art of recycling itself, turning chaos into creation. From the remnants of shattered stars, new solar systems emerge, planets form, and life finds a way. It's a story of resilience written in the fabric of space itself, and it's happening right now, in the distant corners of the cosmos. But how does it all work? How can something as destructive as a supernova give birth to new worlds? That's the mystery we're about to unravel. Together, we'll journey through the life cycles of galaxies, witness the explosive deaths of stars, and discover how cosmic dust weaves itself into the building blocks of new celestial wonders. By the end of this exploration, you'll never look at the night sky the same way again, because the universe isn't some frozen snapshot. It's a living, breathing entity, constantly reinventing itself. And the most astonishing part, we're all part of this grand cosmic dance. So, are you ready to step into the story? Let's begin. The secret to galactic rebirth lies in the delicate balance between chaos and creation. Think of it like a cosmic phoenix. When massive stars reach the end of their lives, they don't just vanish in silence. Instead, they go out with a bang, erupting in supernovas so powerful they outshine entire galaxies for weeks. These explosions do something extraordinary. They blast heavy elements like carbon, oxygen, and iron across interstellar space, seeding the cosmos with the raw materials for new stars, planets, and even life itself. It's as if the universe is constantly tearing down its old structures to build something new from the wreckage. But supernovae are just one piece of the puzzle. At the centers of most galaxies lurk supermassive black holes, gravitational monsters that play a surprising role in this cycle. While they famously devour anything that comes too close, they also act like cosmic engines, spewing out jets of energy that heat surrounding gas clouds. This violent energy actually prevents stars from forming too quickly, regulating the galaxy's growth like a cosmic thermostat. Then, when galaxies collide, a slow-motion dance that can take millions of years, the shockwaves compress these gas clouds, triggering bursts of new star formation. It's almost poetic. The same forces that destroy also create, ensuring the universe never stagnates. And here's the mind-blowing part. This isn't some rare event. Our own Milky Way is currently on a collision course with the Andromeda galaxy, a merger that will reshape both in about 4 billion years. Yet instead of total destruction, simulations show these collisions often lead to a rebirth, smaller galaxies combining into larger, more complex structures. Even now, telescopes capture distant galaxies in various stages of this cycle, from the ragged edges of ones recently torn apart to the vibrant spirals where new stars are bursting into existence. The universe isn't just enduring, it's thriving, constantly reinventing itself through these magnificent, chaotic processes. Consider the life of a massive star, a cosmic giant burning bright with the fury of nuclear fusion. For millions of years, it radiates light and heat, but when its fuel runs out, the real spectacle begins. In its final moments, gravity wins the battle against outward pressure, and the star collapses inward in a fraction of a second. Then boom, the shockwave rebounds in a supernova explosion so powerful it can briefly outshine every star in its host galaxy combined. This isn't just a fireworks display for the cosmos. A supernova is the universe's ultimate recycler. The sheer energy of the blast fuses atoms together, creating heavy elements like gold, platinum, and uranium, materials that never existed inside the star during its lifetime. These newly forged elements are hurled into space at incredible speeds, mixing with vast clouds of gas and dust. Over time, gravity pulls these enriched clouds together, forming the next generation of stars and planets. Without these violent stellar deaths, Earth and everything on it wouldn't exist, but the story doesn't end there. The supernova's aftermath is just as fascinating. Depending on the star's size, the explosion leaves behind either a neutron star, an object so dense a teaspoon of it would weigh 1 billion tons, or a black hole where gravity is so strong not even light can escape. These remnants become cosmic powerhouses, shaping their surroundings in unexpected ways. Neutron stars spin rapidly, emitting beams of radiation that sweep across space like lighthouse beacons. Black holes, though infamous for their appetite, can also trigger star formation by compressing nearby gas clouds with their gravitational pull. What's truly remarkable is how interconnected this cycle is. The iron in your blood, the calcium in your bones, even the silicon in your phone, all were forged in the hearts of dying stars and scattered across the galaxy by supernovae long before our solar system was born. Every time you look up at the night sky, you're witnessing an ongoing story of destruction and renewal, where the end of one star marks the beginning of countless others. Black holes might seem like the ultimate villains of the cosmos' bottomless pits where matter vanishes forever. But here's the twist. These gravitational behemoths are also master builders, shaping galaxies in ways we're only beginning to understand. At the heart of nearly every large galaxy, including our own Milky Way, lurks a supermassive black hole, and far from being mere destroyers, they act like cosmic architects, controlling the pace of star formation with almost surgical precision. Take those blazing jets of energy shooting from a black hole's poles at nearly the speed of light. While they sound destructive, these jets actually serve a surprising purpose. As they plow through surrounding gas clouds, they heat the material to staggering temperatures, preventing it from cooling and collapsing into new stars. It's like a celestial thermostat. When star formation runs too hot, the black hole steps in to slow things down. Without this regulation, galaxies would burn through their fuel too quickly, leaving behind barren wastelands instead of vibrant stellar nurseries. Yet in other cases, black holes do the opposite. They spark creation. When those same energy jets slam into distant gas clouds, the shock waves can compress the material, triggering sudden bursts of star birth far from the galactic center. Imagine a sculptor who both chips away at marble and molds new shapes from the fragments. That's a black hole's dual role in galactic evolution. Even their gravity, often depicted as purely destructive, can stir galactic gas like a spoon in coffee, mixing elements needed for future stars and planets. Perhaps the most stunning example lies in galaxy collisions. When two galaxies merge, their central black holes eventually spiral toward each other, releasing gravitational waves that ripple through space-time. But before they collide, their gravitational dance churns the galactic soup, funneling gas into dense pockets where new stars ignite like fireworks. The resulting galaxy, often larger and more structured than its predecessors, bears the fingerprints of these invisible architects. Far from bringing chaos, black holes impose order, ensuring galaxies don't just survive but evolve into something grander. So the next time you picture a black hole, don't just see a void, see a cosmic conductor, orchestrating the rise and fall of stars across billions of years. Without them, the universe might lack the rhythm that turns destruction into rebirth and chaos into breathtaking complexity. Picture two galaxies drifting through the cosmic void, drawn together by the invisible threads of gravity. At first, the dance is slow. Millions of years pass as their spiral arms stretch toward one another, warping under the relentless pull. Then comes the moment of collision, a spectacle of chaos and creation unfolding on a scale so vast it defies imagination. Stars don't crash into each other. Space is too vast for that, but their orbits are flung into disarray, painting swirling streaks of light across the darkness. This isn't destruction, it's transformation. As the galaxies merge, their interstellar gas clouds slam together, compressing under the force of the impact. Like striking a match in a room full of kindling, these collisions ignite furious bursts of star formation. Suddenly, pockets of gas collapse under their own gravity, lighting up as brilliant blue clusters of newborn stars. Telescopes have captured these stellar nurseries in merging galaxies, glowing like diamonds scattered across velvet. The iconic antennae galaxies, locked in a slow-motion collision, are smothered in such regions, proof that chaos breeds new life. Yet the most fascinating part isn't the fireworks, it's what happens afterward. Over billions of years, the two galaxies settle into a new, unified shape. Spirals often become ellipticals, smooth and featureless, but brimming with middle-aged stars. The gas and dust that fueled the star-forming frenzy is either used up or blown away, leaving behind a galaxy reborn. Even the supermassive black holes at their cores eventually spiral together, merging in a final gravitational crescendo that sends ripples through space-time itself. And here's the kicker, our own Milky Way is living proof of this cycle. Its halo is littered with the remnants of smaller galaxies it's absorbed over eons, like cosmic fingerprints of past mergers. In about 4 billion years, it'll face its greatest transformation yet when Andromeda, a galaxy twice its size, comes calling. Simulations show the two will entwine, their stars flung into new orbits, their gas colliding to spark a fresh wave of stellar birth. The resulting galaxy, nicknamed Andromeda, will be something entirely new, a testament to the universe's endless ability to reinvent itself. So the next time you hear about galaxies colliding, don't think of it as an ending. Think of it as a cosmic renovation where the rubble of the old becomes the foundation of the new. These mergers aren't accidents. They're the universe's way of stirring the pot, ensuring that galaxies don't just exist but evolve. From the chaos comes beauty, from destruction comes rebirth, and from the dance of giants comes the next chapter in an epic written in starlight. Imagine trying to build a house without a foundation. The walls would crumble, the roof would collapse, and the structure would fly apart. Now picture our universe without dark matter. Galaxies, those glittering islands of stars, would simply disintegrate, their stars scattering into the void like sand in the wind. This invisible force, completely undetectable except through its gravitational pull, is the hidden framework that holds the cosmos together. It's the silent architect behind every galactic collision, every stellar rebirth, and every cosmic cycle we've explored. Dark matter doesn't just exist, it dominates. Scientists estimate it makes up about 85% of all matter in the universe, outweighing the atoms we can see by nearly 6 to 1. Its gravity molds galaxies into shape, wrapping around them like an unseen hand guiding their growth. When galaxies collide, it's often the dark matter that dictates the choreography, its gravitational pull determining how stars and gas clouds will rearrange. Without it, the Milky Way would spin so fast it would fling stars into deep space, and the majestic spirals we admire through telescopes would unravel into cosmic confetti. Yet for all its power, dark matter remains one of science's greatest enigmas. It doesn't emit, absorb, or reflect light, hence the name. We can't photograph it, trap it, or even say for certain what it's made of. But its fingerprints are everywhere. When astronomers map the gravity of distant galaxies, they find far more mass than visible stars and gas can account for. When they study how light bends around galaxy clusters, the distortion reveals vast halos of dark matter warping space itself. Even the cosmic microwave background, the afterglow of the Big Bang, bears the imprint of dark matter's gravitational influence. Here's where it gets even more fascinating. Dark matter doesn't just hold galaxies together, it shapes their very evolution. In the early universe, tiny fluctuations in dark matter density acted like cosmic seeds, gathering gas and dust into the first protogalaxies. Over billions of years, these clumps merged and grew, with dark matter providing the gravitational glue. Today, it continues to steer galactic collisions, ensuring that when galaxies merge, they don't just scatter into chaos but reorganize into new, stable structures. So while stars may be the glittering actors on the cosmic stage, dark matter is the stage itself, unseen, uncredited, but utterly essential. Without it, the cycles of destruction and rebirth would grind to a halt, and the universe as we know it would cease to exist. Solving the mystery of dark matter isn't just about filling a gap in our knowledge, it's about uncovering the hidden rules that govern the grandest story ever told, the story of existence itself. Every galaxy begins as little more than a whisper in the cosmic dark, an enormous cloud of hydrogen gas and dust, so diffuse it would seem like empty space to our eyes. But gravity is patient. Over millions of years, it tugs at these scattered particles, drawing them closer until the cloud begins to collapse under its own weight. As it shrinks, pockets of denser gas form, growing hotter until ignition. The first stars burst into life, their nuclear furnaces lighting up the darkness. This is a galaxy's infancy, a time of chaotic brilliance where young stars blaze fiercely and die young, seeding their surroundings with heavier elements. As the galaxy matures, something remarkable happens. Order emerges from the chaos. The remaining gas settles into a spinning disk, while stars organize into sweeping spiral arms or smooth ellipses. New stars form at a steadier pace, no longer the frantic bursts of youth but a more measured rhythm. Planetary systems take shape around these stars, and in at least one extraordinary case, our own solar system life emerges. This is the galaxy's golden age, a period of stability that can last for billions of years. But like all things in the universe, it doesn't last forever. The turning point comes when the galaxy's fuel begins to run low. Star formation slows as the remaining gas is either locked up in stars or blown away by stellar winds and supernova. Some galaxies, like our Milky Way, continue forming stars at a trickle, while others, especially massive ellipticals, become cosmic retirement homes filled with aging stars and little activity. But even in this quiet phase, galaxies aren't done shaping the universe. Their supermassive black holes may awaken, spewing jets of energy that heat surrounding gas and regulate star formation across entire galaxy clusters. Then comes the finale, or what seems like it. Galaxies rarely die alone. Drawn together by gravity, they collide in spectacular mergers that should, by all rights, tear them apart. Yet instead of destruction, these collisions often trigger rebirth. The shock waves compress remaining gas, sparking new waves of star formation. The merged galaxy, now larger and more complex, begins a new chapter, one that might see it joining an even bigger galactic community. And so the cycle continues, with each generation building on the last. The beauty of this process lies in its efficiency. Every element forged in a dying star, every wisp of gas ejected in a supernova, becomes raw material for the next cosmic era. Our own existence is proof of that. The carbon in our cells, the oxygen we breathe, all were once scattered across the galaxy by long-dead stars. In this way, galaxies aren't just objects in space, they're living histories, carrying the story of the universe forward one stellar generation at a time. Far from being endpoints, their so-called deaths are merely transitions turning the page for the next act in an epic that has no final chapter. Our Milky Way galaxy isn't just our cosmic home, it's a living history book, its spiral arms filled with clues about a dramatic past most of us never realized. Right now, as you look up at the night sky, you're seeing light from stars that carry echoes of ancient galactic collisions. Because long before Earth existed, our galaxy was already growing through violent encounters. The evidence surrounds us: streams of stars stretching far beyond the Milky Way's disk-like celestial ribbons, remnants of smaller galaxies torn apart by our galaxy's gravity over billions of years. One of the most famous examples is the Gaia Enceladus galaxy, a dwarf galaxy that collided with the Milky Way around 8 to 11 billion years ago. When astronomers studied the motions and compositions of certain stars, they found an entire population moving differently, the cosmic equivalent of spotting strangers at a family reunion. These stars had higher levels of heavy elements, revealing they formed in a separate galaxy before being absorbed. Today, their descendants still orbit through our galaxy's halo, silent witnesses to that primeval merger that helped shape the Milky Way into what we see today. But the Milky Way didn't stop growing. Even now, it's digesting the Sagittarius dwarf spheroidal galaxy, whose stars are being slowly pulled into our galaxy's vast gravitational embrace. Telescopes have mapped these stars in long, looping trails that wrap around the Milky Way like cosmic tinsel. Each merger, no matter how small, leaves its mark, adding stars, altering orbits, and sometimes triggering bursts of new star formation as incoming gas clouds collide with our own. Now fast forward 4.5 billion years. The Andromeda galaxy, currently a faint smudge in our night sky, will loom larger as it drifts closer. Unlike previous mergers with smaller galaxies, this will be a collision of cosmic titans. Computer simulations show the two spirals will first pass through each other, their gravity stretching both galaxies into bizarre, warped shapes. Stars won't collide. Space is too vast, but their orbits will be flung into chaos, painting swirling streaks across the sky. Then, over hundreds of millions of years, they'll swing back for a final embrace, merging into a single, larger galaxy. Astronomers nickname Andromeda. Here's what's truly remarkable: this merger won't destroy either galaxy, but transform them. The violent interaction will compress remaining gas clouds, igniting a new wave of star formation, even as the original spiral structures fade. Eventually, the chaos will settle, leaving behind an elliptical galaxy, smooth, featureless, but brimming with middle-aged stars. Our solar system will likely be flung farther from the galactic center, but otherwise unharmed. The night sky from Earth, if any humans remain to see it, will be utterly different. No Milky Way band, no Andromeda smudge, just a sky filled with stars from two merged galaxies. This grand transformation mirrors countless mergers we observe across the universe, confirming our galaxy isn't special, it's part of the same cosmic cycle playing out everywhere. By studying the Milky Way's past and future, we're not just learning about our home, we're reading the universe's playbook, understanding how galaxies grow, evolve, and reinvent themselves over eons. Every collision, every burst of star formation, every quiet period is part of an endless dance, one where destruction always gives way to new creation, and endings are merely preludes to the next cosmic chapter. Deep in the heart of the Phoenix Cluster, nearly 5.8 billion light-years from Earth, a cosmic miracle unfolds. This isn't just another group of galaxies, it's a stellar resurrection in action, defying everything we thought we knew about galactic life cycles. At its center lies a supermassive black hole behaving unlike any other, temporarily abandoning its role as a cosmic killjoy and instead permitting an unprecedented rebirth. For decades, astronomers assumed the centers of galaxy clusters were stellar graveyards, places where supermassive black holes spewed so much energy they boiled away the raw materials for new stars. The Phoenix Cluster shattered that assumption. Here, despite the black hole's overwhelming presence, star formation has erupted at a rate of about 700 new stars per year, nearly 20 times faster than our Milky Way. It's as if the universe pressed pause on destruction and allowed creation to run wild. The secret lies in the delicate balance between heating and cooling. Normally, energy jets from the central black hole keep cluster gas too hot to collapse into stars. But in Phoenix, something extraordinary happened. The hot gas began cooling faster than the black hole could reheat it. Like a pot boiling over, this cooled gas cascaded toward the cluster's core, collapsing into dense clouds where gravity could work its magic. The result: a firestorm of stellar birth lighting up the cosmic darkness. What makes this even more remarkable is the timescale. The Phoenix Cluster's rebirth phase won't last forever, perhaps just 100 million years, a blink in cosmic terms. But during this brief window, it's giving us a front-row seat to a process normally hidden by billions of years. We're witnessing what our own Milky Way might have experienced during past growth spurts, and what future galaxies will undergo long after humanity is gone. This celestial phoenix teaches us a profound lesson about the universe's resilience. Even in environments dominated by destructive forces, the potential for renewal never disappears. It merely waits for the right conditions. The same black holes that suppress star formation can, through their absence of action, become unwitting midwives to new generations of stars. The cycle continues, not in spite of the chaos, but because of it, a reminder that in the grand tapestry of the cosmos, endings and beginnings are often the same thread seen from different angles. Those shimmering veils of gas and dust we call nebulae aren't just beautiful cosmic decorations. They're the universe's ultimate recycling centers, where stardust literally becomes starlight all over again. Picture a vast cloud of hydrogen, helium, and heavier elements drifting through space, so diffuse you could pass through it without noticing. But gravity works its magic over millions of years, pulling these particles together until pockets become dense enough to collapse under their own weight. The temperature rises, pressure builds, and suddenly nuclear fusion ignites. A new star flares to life, its birth cry written in the very fabric of the nebula that created it. The Orion Nebula gives us a front-row seat to this celestial nursery in action. Just 1,500 light-years away, this swirling mass of gas and dust glows with the energy of newborn stars. The Hubble Space Telescope has captured stunning details: proplyds, or protoplanetary disks, forming around infant stars, while massive young stars blast ultraviolet radiation that sculpts the surrounding gas into fantastical shapes. It's like watching a stellar maternity ward with stars at every stage of development. Some are still shrouded in dusty cocoons, while others have blown away their birth clouds, shining bright enough to ionize the surrounding hydrogen into that iconic red glow. But here's what makes nebulae truly special. They're built from the ashes of their predecessors. When massive stars die in supernova explosions, or when aging sun-like stars gently shed their outer layers as planetary nebulae, they return enriched material to the cosmos. Elements like carbon, nitrogen, and oxygen, the building blocks of planets and life itself, get mixed back into the interstellar medium. The Eagle Nebula's famous pillars of creation aren't just incubating new stars, they're made of recycled stardust from generations long gone. This cosmic circle of life ensures that every new star system starts with a richer chemical palette than the last. Some nebulae take this recycling to extremes. In the Tarantula Nebula, located in the Large Magellanic Cloud, we see a frenzy of stellar birth and death playing out on an epic scale. This region hosts some of the most massive stars known, burning bright and dying young in supernova that shock surrounding gas clouds into collapsing into the next generation. It's a stellar assembly line where death fuels new creation at a breathtaking pace. The energy released by these stars carves out vast bubbles in the nebula, whose surfaces become prime real estate for triggering even more star formation. Without these glowing stellar nurseries, galaxies would eventually run out of fuel. Stars would age and die, but their materials would remain locked away, unable to form new celestial bodies. Nebulae are the universe's way of keeping the cycle going, transforming the remnants of dying stars into the seeds of new ones. They're proof that in the cosmos, nothing truly ends, it just changes form, taking on new roles in an endless dance of destruction and rebirth. Every atom in your body likely passed through multiple nebulae before becoming part of our solar system, linking you directly to stars that shone billions of years before Earth existed. Quasars blaze across the cosmos like celestial lighthouses, their brilliance outshining entire galaxies from billions of light years away. At first glance, they seem like pure engines of destruction, supermassive black holes gorging on stars and gas, spearing the void with jets of radiation powerful enough to strip planets of their atmospheres. But hidden within their fiery hearts lies a paradox. These cosmic monsters don't just erase galaxies, they reshape them, clearing the slate for future rebirth in ways we're only beginning to understand. Take the quasar known as 3C273, for example. Nestled in a galaxy over 2 billion light-years away, its central black hole devours matter so voraciously that the resulting energy could boil away Earth's oceans in seconds. The radiation pressure from quasars like this is so intense, it acts like a cosmic sandblaster, pushing gas and dust out of the galaxy at millions of miles per hour. Without this raw material, star formation grinds to a halt, a process astronomers call quenching. For a time, the galaxy becomes a stellar desert, its remaining stars aging under the quasar's unforgiving glare. Yet this isn't the end of the story. When quasars eventually exhaust their fuel supply, sometimes after hundreds of millions of years, something remarkable happens. The once banished gas, now cooled and enriched with heavy elements from the quasar's fury, begins to trickle back inward. Freed from the radiation's grip, these returning clouds collapse under gravity, igniting new waves of star formation. It's as if the quasar's destruction was just the universe's way of pressing reset, a violent but necessary step in the galaxy's evolution. The evidence is written in the skies. Astronomers have spotted post-quasar galaxies where star birth has reignited with surprising vigor. In some cases, the returning gas forms orderly rings or spirals, creating ideal conditions for stable, long-lived stellar nurseries. The black hole, now quieter but still present, transitions from tyrant to regulator, its occasional outbursts preventing star formation from running wild. The galaxy emerges from its trial by fire not weaker, but transformed, its structure altered, its chemistry enriched, its future rewritten. Perhaps most astonishing is how quasars shape their surroundings far beyond their host galaxies. Those high-speed jets, stretching thousands of light-years, plow into neighboring gas clouds like cosmic plows. At first, they heat and disrupt, but over time, the compressed edges of these clouds can collapse into new stars, some of which may eventually fall back into the quasar's galaxy, seeding it with fresh material. Even in their most destructive phase, quasars are laying groundwork for renewal on scales we're only starting to map. So while quasars may seem like the ultimate cosmic wrecking balls, they're really more like gardeners pruning galaxies so they can regrow in healthier forms. Their violence isn't mindless. It's part of a grand cycle where even the most extreme phenomena serve a purpose. Across billions of years, these brilliant beacons have guided galaxies through phases of death and rebirth, proving once again that in the universe, destruction and creation are two sides of the same coin. Messier 87 looms in the Virgo cluster like a cosmic relic, a massive elliptical galaxy glowing with the dull red light of aging stars. Unlike our Milky Way, with its vibrant spiral arms birthing new stars, this giant appears frozen in time, its gas supplies long since exhausted. Astronomers call galaxies like these red and dead, their stellar populations quietly fading over billions of years. But looks can deceive. Even these seemingly lifeless giants hold secrets and potential futures that defy their sleepy appearances. The key lies in their environment. Galaxies like Messier 87 often reside at the hearts of dense clusters where they've spent eons cannibalizing smaller neighbors. All those past mergers left them bloated with stars but starved of the cold gas needed to create new ones. Yet the universe loves a second act. Should fresh gas streams wander too close, perhaps from a cosmic filament or a gas-rich dwarf galaxy, the sleeping giant could awaken. Gravity would compress the new fuel, igniting pockets of star formation like embers catching a sudden breeze. Mergers offer another path to rebirth. When two dead ellipticals collide, their combined gas reserves, though sparse, can become dense enough to trigger a late-life burst of stellar creation. Computer simulations show these slow-motion collisions can churn up long-dormant material, mixing it just enough to spark new activity. The resulting galaxy might never regain the glory of its youth, but it wouldn't stay red and dead forever. Perhaps the most surprising twist comes from supermassive black holes. These silent sentinels at galactic centers, once thought to only suppress star formation, can sometimes do the opposite. If gas falls in at just the right rate, not too fast to be blasted away by radiation, but not too slow to be heated indefinitely, it can cool into star-forming clouds. It's a delicate balance, but when it happens, even aging galaxies get a chance to rewrite their final chapters. So when we peer at these dead galaxies through telescopes, we're not looking at endings, we're seeing intermissions. The universe abhors stagnation, and given enough time, even the quietest corners find ways to reinvent themselves. Whether through stolen gas, dramatic collisions, or the subtle influence of black holes, the cycle continues. After all, in a cosmos where destruction and rebirth are two sides of the same coin, nothing truly dies. It just waits for the right moment to begin again. Stretching across the unimaginable voids between galaxies lies a hidden network of matter, so thin you could fly a spaceship through it for light years without noticing, yet so vast it contains most of the ordinary matter in the universe. This intergalactic medium isn't just empty space. It's the ultimate cosmic recycling plant, where atoms expelled from dying stars and galaxies await their next chapter. Picture it like an enormous, invisible river system, with currents of hydrogen and helium flowing along filaments of dark matter, the cosmic web that structures the entire universe. When galaxies collide or supernova blast material outward, much of that matter doesn't simply vanish. Instead, it joins this intergalactic reservoir, drifting for millions or even billions of years until gravity pulls it into a new galactic home. The Magellanic Stream, a faint ribbon of gas trailing our Milky Way, offers a stunning nearby example. This 300,000 light-year-long river of hydrogen was torn from the small and large Magellanic Clouds as they orbit our galaxy. Eventually, that gas will rain down onto the Milky Way's disk, fueling future generations of stars. It's a slow-motion recycling process happening right in our cosmic backyard. But the real magic happens on much larger scales. Galaxy clusters, those metropolises of the cosmos, are surrounded by vast atmospheres of million-degree gas, so hot it glows in X-rays rather than visible light. When galaxies within these clusters move, they can leave behind tails of gas like cosmic breadcrumbs. The Virgo cluster, for instance, shows galaxies with stripped gas tails stretching hundreds of thousands of light years. That material doesn't disappear, it joins the cluster's hot atmosphere, where it may eventually cool and fall back onto other galaxies in a process astronomers call galactic recycling. Even more astonishing are the cosmic fountains some galaxies create. When supermassive black holes become active, their energy jets can launch gas far beyond a galaxy's boundaries. At first, this seems like pure loss, but simulations show much of that material eventually slows, cools, and falls back in a spectacular rain of star-forming fuel. The M87 galaxy, with its famous black hole jet, might be doing exactly this on a colossal scale. What looks like destruction is actually part of a galactic water cycle, where matter evaporates into intergalactic space only to condense back later. The universe's efficiency puts even the most advanced human recycling systems to shame. Every atom expelled by a dying star, every wisp of gas torn away in a galactic collision, remains part of an intricate cycle that spans billions of years. This intergalactic exchange program ensures that galaxies never truly run out of fuel. They just have to wait for the cosmic conveyor belt to bring it back around. The result, a universe where nothing is ever truly wasted, and every ending carries the seeds of new beginnings. Magnetic fields weave through galaxies like invisible threads, quietly shaping their destinies in ways we're only beginning to understand. While gravity gets all the attention for sculpting cosmic structures, these subtle forces work behind the scenes, guiding the flow of gas with the precision of cosmic traffic controllers. Picture a spiral galaxy's arms, not just beautiful swirls of stars, but highways of magnetic influence where gas clouds align along field lines like iron filings around a magnet. This hidden architecture determines whether a cloud will collapse into new stars or remain suspended in space, waiting for its moment. Take the Whirlpool Galaxy, a stunning face on spiral just 23 million light-years away. When astronomers mapped its magnetic field using radio telescopes, they discovered something astonishing. The field lines trace the spiral arms perfectly, stronger where star formation is most intense. These magnetic channels appear to funnel gas efficiently into stellar nurseries, accelerating the birth of new suns. But in other galaxies, like the massive elliptical Messier 87, the fields behave differently, creating turbulent zones that actually slow star formation by preventing gas from cooling and collapsing. The secret lies in how magnetic fields interact with cosmic turbulence. Imagine trying to pour cream into coffee while stirring vigorously. The cream disperses chaotically. That's gas without magnetic fields. Now imagine the cream contains thousands of tiny straws all aligned in the same direction. The liquid flows more smoothly along those channels. That's what magnetic fields do for interstellar gas, reducing turbulence and allowing dense cores to form more easily. In the Orion molecular cloud, where new stars are forming right now, measurements show magnetic fields strong enough to support gas clouds against their own gravity, essentially putting star formation on pause until the fields weaken or the clouds gather more mass. Yet these fields aren't static, they evolve alongside their galaxies. When supernovae explode, their shockwaves can tangle magnetic fields like spaghetti, creating chaotic regions where star formation becomes unpredictable. Galactic collisions take this further, stretching and amplifying fields until they become powerful enough to influence the merger's entire outcome. The antennae galaxies, locked in their spectacular collision, showcase magnetic fields 10 times stronger than our Milky Way's fields that now guide the rebirth of this system by channeling gas into specific regions where new stars will eventually light up. Perhaps most fascinating is how magnetic fields connect the small to the enormous. The same forces that align dust grains in a dark nebula also shape galactic-scale winds blowing between galaxies. When active black holes launch jets of plasma, they carry twisted magnetic fields that can influence gas flows millions of light-years away. Even the cosmic web, the vast network of filaments connecting galaxy clusters, shows evidence of magnetic fields that may have guided the universe's first stars into existence. Far from being passive features, magnetic fields are active participants in the cycle of galactic death and rebirth. They determine which gas clouds become stars and which remain dormant, which mergers spark stellar fireworks and which fizzle quietly. Like invisible conductors of a cosmic orchestra, they don't play the instruments, they shape how the music unfolds. And as we learn to map these fields across the universe, we're discovering that to truly understand galactic evolution, we must learn to see not just with light, but with magnetic eyes. Cosmic rays are the universe's invisible matchmakers, particles racing through space at nearly the speed of light with enough energy to kickstart the birth of stars. These aren't gentle rays of sunlight, they're atomic nuclei stripped of electrons, accelerated to extreme velocities by supernova shockwaves and other violent cosmic events. When one of these high-speed particles slams into a cold, dark gas cloud, it doesn't just pass through, it leaves a trail of ionized gas in its wake, stripping electrons from atoms and fundamentally changing the cloud's chemistry. This ionization process might seem destructive, but it's actually the first step in stellar creation. Neutral hydrogen gas, the primary ingredient for star formation, resists collapsing under gravity because its atoms repel each other slightly. But when cosmic rays ionize that gas, creating positively charged protons and free electrons, everything changes. The charged particles interact differently, allowing gravity to overcome resistance and pull the cloud inward. It's like turning a room full of people who barely notice each other into a crowd suddenly holding hands. The connections make it easier to move as one. The proof is written in stellar nurseries across our galaxy. In regions like the Orion molecular cloud, astronomers have detected higher cosmic ray fluxes coinciding with active star-forming zones. The correlation isn't accidental. These high-energy particles are essentially jump-starting the collapse process. Even more telling are dark clouds, dense pockets of gas that should be forming stars but remain mysteriously quiet. Measurements show these regions often have lower cosmic ray penetration, their star-forming potential literally frozen in place without these energetic triggers. But cosmic rays don't just initiate star birth, they influence the entire life cycle. As a gas cloud collapses, cosmic rays continue bombarding it, maintaining enough ionization to prevent the magnetic fields within from becoming too strong. This delicate balance is crucial. If fields grow too powerful, they can support the cloud against gravity indefinitely, putting star formation on hold. The rays essentially keep the magnetic pressure valve open just enough for collapse to proceed. Later, when young stars ignite, their intense radiation would normally blow away remaining gas, limiting their growth. But cosmic rays help by keeping some gas ionized and magnetically coupled, allowing stars to keep feeding longer. The most fascinating aspect might be the cosmic ray time delay. These particles don't travel in straight lines. Galactic magnetic fields curve their paths into spirals, meaning a single cosmic ray might wander for hundreds of thousands of years before hitting a gas cloud. This creates a built-in lag between a supernova's explosion and its impact on future star formation. It's nature's way of spacing out stellar generations, ensuring new stars don't all form at once but in waves spread across eons. When we see a cluster of young stars today, their birth may have been triggered by cosmic rays from a stellar death that occurred long before our solar system even existed. Without these invisible catalysts, the universe would be a very different place. Star formation would rely solely on slow, random gas collisions, reducing the rate of stellar births dramatically. Galaxies might never achieve the vibrant spiral structures we see today, their gas remaining locked in formless clouds. Even life as we know it could be affected. Fewer stars mean fewer planets, and less enrichment from supernova means fewer heavy elements for rocky worlds. From the largest galactic scales down to the atoms in our bodies, cosmic rays are the unsung heroes of cosmic recycling, turning destruction into creation one high-speed particle at a time. Hidden behind the thick veil of dust near the Milky Way center lies one of the universe's most perplexing enigmas, the Great Attractor. This colossal gravitational anomaly exerts a pull so powerful it's dragging our entire galaxy, along with thousands of others, toward it at over 600 kilometers per second. But what could possibly possess such overwhelming influence? The answer may rewrite our understanding of cosmic destiny. For decades, astronomers struggled to study this region directly because our own galaxy's bulge blocks the view. But infrared and radio telescopes eventually pierced the dust, revealing a startling truth: the Great Attractor isn't a single massive object, but a dense confluence of galaxy clusters centered around the Norma cluster. This Laniakea supercluster, as it's now called, acts as a gravitational anchor for over 100,000 galaxies in our cosmic neighborhood. Like water spiraling toward a drain, galaxies across an unfathomable volume are flowing toward this point in a slow-motion migration that will take billions of years to complete. The implications for galactic rebirth are profound. As galaxies stream toward this gravitational focal point, their paths intertwine in an intricate dance. Some will merge violently, triggering bursts of star formation like we've seen in other collisions. Others will swing past each other in close encounters that distort their shapes and strip away gas. Over time, the Great Attractor's pull will reshape the entire local universe, concentrating matter in ways that may birth entirely new superclusters, cosmic metropolises that don't even exist yet. What makes this phenomenon truly fascinating is its role in the larger cycle. The Great Attractor isn't unique. Similar gravitational focal points likely exist throughout the universe, each orchestrating galactic motions on incomprehensible scales. Together, they form a hierarchy of flows that redistribute matter across cosmic time. Galaxies consumed by one attractor may eventually find their atoms recycled into new structures elsewhere, continuing the eternal loop of destruction and renewal. Yet mysteries remain. Recent observations suggest something even larger lies beyond the Great Attractor. The Shapley supercluster, 8 times more massive, may be the ultimate destination in this cosmic cascade. As we map these flows with increasing precision, we're glimpsing the universe's grand choreography, a ballet where gravity writes the steps and galaxies dance to the rhythm of rebirth across billions of years. Far from random, their motions reveal an order hidden in plain sight, proving once again that in the cosmos, even destruction follows patterns that lead to new beginnings. Galactic cannibalism sounds like something out of a cosmic horror story, but in reality, it's one of the universe's most elegant recycling programs. Picture a massive spiral galaxy like our Milky Way, its gravity reaching out like invisible tendrils, slowly pulling in smaller dwarf galaxies that wander too close. Over billions of years, these captured galaxies are torn apart, their stars and gas absorbed into the larger structure. It's not a violent feast, but a slow, inevitable merging, like a river dissolving a sugar cube. Our own galaxy is a prime example of this process in action. The Milky Way's halo, a vast, diffuse sphere of stars surrounding its bright disk, is littered with the remnants of past meals. Take the Gaia Enceladus galaxy, a dwarf galaxy that collided with ours nearly 10 billion years ago. Today, its stars are strewn across our halo, their orbits telling the story of that ancient merger. Then there's the Sagittarius dwarf spheroidal, currently in the process of being dismantled, its stars streaming into the Milky Way in long, looping ribbons. These mergers aren't just historical footnotes, they're how our galaxy grew into the grand spiral we see today. But here's the twist, while the smaller galaxy gets absorbed, it's far from a one-sided destruction. The incoming stars and gas actually reshape the larger galaxy in subtle ways. When a dwarf galaxy merges, its gravity tugs on the Milky Way's disk, creating ripples that can trigger new star formation. The fresh gas it brings, often untouched by previous generations of stars, acts like a cosmic fertilizer, enriching the galaxy with pristine material for future stellar births. Even the dark matter halos of the two galaxies combine, altering the gravitational landscape in ways that influence how stars and gas move for eons afterward. The most stunning evidence of this process lies in the outskirts of giant galaxies, where astronomers have found shell structures, nested layers of stars left behind like tree rings, each marking a past merger. These shells form when a smaller galaxy is torn apart, its stars sloshing back and forth through the larger galaxy's gravitational field before settling into these distinct patterns. The Sombrero Galaxy, with its spectacular edge on Dust Lane, displays these shells clearly, a visible record of its cannibalistic history. Far from being a destructive act, galactic cannibalism is a creative force. Without it, large galaxies would starve, their gas supplies dwindling over time as stars lock away material in their cores. By consuming smaller neighbors, they gain fresh fuel and new stellar populations, ensuring they don't just survive, they evolve. Even the Milky Way's majestic spiral arms might owe their existence to past mergers that stirred up its gas, creating the density waves that shape its iconic structure. So the next time you hear about a galaxy being eaten, remember, it's not an end but a transformation. The stars from those dwarf galaxies live on, their light now part of a grander tapestry. And somewhere in the distant future, our own Milky Way will meet the same fate swallowed by the even larger Andromeda galaxy, their merger creating something entirely new. In the cosmos, even cannibalism is just another word for rebirth. Dwarf galaxies may be small, but don't let their size fool you. These cosmic underdogs are the unsung heroes of galactic evolution. Picture them as the bricks in a vast celestial construction project, each one contributing to structures far grander than themselves. While giant spirals like Andromeda or the Milky Way dominate our attention, It's often the dwarfs that supply the raw materials, the fresh gas, and even the gravitational nudges that shape the universe as we know it. Take the Large Magellanic Cloud, our Milky Way's largest satellite galaxy. Though just 1/10 its size, this dwarf is far from insignificant. Its gravitational pull is slowly warping our galaxy's outer disk, creating ripples that trigger pockets of star formation. Meanwhile, its gas clouds rich with elements forged in earlier stellar generations drift toward the Milky Way, destined to fuel future stars. This isn't just a one-way relationship. The dwarfs give as much as they take, their interactions weaving an intricate dance of creation and destruction. Yet not all dwarf galaxies meet such gentle fates. Some, like the Canis Major Dwarf, are being unraveled by tidal forces, their stars strewn across space in shimmering streams. These tidal streams aren't just cosmic debris, they're fingerprints of the Milky Way's growth, tracing paths of past mergers like breadcrumbs through time. Telescopes have spotted dozens of these stellar rivers in our galaxy's halo, each one the remains of a dwarf galaxy consumed billions of years ago. The Phoenix Stream, discovered in 2018, stretches over 50,000 light-years, a ghostly reminder of a galaxy sacrificed to our own. What's truly remarkable is how these tiny galaxies defy expectations. Ultra-faint dwarfs, some containing just a few hundred stars, challenge our understanding of dark matter. Their dark matter content is so disproportionately high that they behave like cosmic icebergs. What we see is just a fraction of what's there. These faint smudges of light may hold clues to the universe's most elusive substance, their very existence hinting at dark matter's role in shaping galaxies from the smallest to the largest scales. Even in death, dwarf galaxies leave legacies. When they're torn apart, their scattered stars don't vanish, they join the galactic halo, a vast reservoir of ancient stellar wanderers. Their gas, ejected during the disruption, mingles with the interstellar medium, eventually collapsing into new generations of stars. In this way, a dwarf galaxy's end becomes a larger galaxy's beginning, its materials recycled into something new. The universe has no waste, only transformation. So the next time you gaze at the Milky Way's band of light, remember, its brilliance owes much to those unassuming dwarfs, the silent builders of the cosmos. Their stories remind us that in the grand tapestry of the universe, size doesn't dictate significance. From the smallest dwarf to the mightiest spiral, every galaxy plays its part in the endless cycle of destruction and renewal. Every galaxy has a heartbeat, a rhythm of stellar birth that quickens and slows over cosmic time. This pulse, measured in stars born per year, tells us more about a galaxy's health and history than its shape or size ever could. Picture a newborn galaxy in the early universe, bursting with activity as it converts pristine gas into stars at a feverish pace, hundreds, even thousands of new suns igniting annually. Fast forward billions of years, and that same galaxy might produce just 1 or 2 stars per year, its gas reserves depleted by generations of stellar lives and deaths. The most dramatic spikes in this cosmic pulse occur during galactic collisions. When two galaxies merge, their interstellar gas clouds slam together like storm fronts, compressing under unimaginable pressure. The antennae galaxies, locked in a slow-motion collision, showcase this perfectly. Their overlapping regions glow with the blue light of newborn star clusters, each containing thousands of stars younger than 10 million years. For a brief time, these galaxies are producing stars 30 times faster than our Milky Way, turning destruction into creation on a staggering scale. But these bursts are short-lived. As the merger progresses, much of the gas is either blown away by supernova winds or funneled toward the supermassive black holes at their cores, which heat it beyond the point of star formation. Yet mergers aren't the only way to revive a galaxy's star-forming pulse. Some galaxies experience quieter rebirths through cold accretion, streams of pristine gas flowing in from the cosmic web. Unlike recycled gas from supernova, this material hasn't been polluted by previous stellar generations, making it ideal for forming new stars. The spiral galaxy Messier 61 exemplifies this process, its star formation rate noticeably higher than its neighbors thanks to a steady trickle of fresh gas from intergalactic space. It's like a desert cactus suddenly finding itself under a dripping faucet, springing to life after years of drought. On the flip side, nothing quenches star formation quite like an active galactic nucleus. When a supermassive black hole feeds, it doesn't just swallow matter. It spits out energy in the form of radiation and jets that heat surrounding gas to millions of degrees. The galaxy becomes a pressure cooker where gas can't cool enough to collapse into stars. In extreme cases, like the nearby radio galaxy Centaurus A, these jets carve vast bubbles in the interstellar medium, creating dead zones where star formation is impossible for thousands of light years. Astronomers track these rhythms using telltale signatures in a galaxy's light. Young, massive stars flood their surroundings with ultraviolet radiation, causing nearby gas to fluoresce in specific colors. By measuring the intensity of this glow, scientists can count stellar births like a doctor listening to a heartbeat. Other clues come from infrared light, which reveals stars forming deep within dust clouds, and radio waves that trace cold hydrogen gas, the raw fuel for future generations. What emerges from these observations is a revelation: galaxies aren't static islands, but dynamic ecosystems where star formation rises and falls in response to internal and external forces. A galaxy might spend its youth in a frenzy of stellar birth, its middle age in steady production, and its twilight years in quiet decline, only to be rejuvenated by a merger or gas influx billions of years later. The universe doesn't follow a straight path from birth to death, but a spiral of destruction and renewal, where even the faintest pulse can quicken again given the right conditions. And that's the most hopeful lesson of all in the cosmos. As in life, dormancy isn't the same as death. Sometimes it's just a pause between beats. Supermassive black holes might seem like the ultimate cosmic drains, swallowing everything that ventures too close, but their true role in galactic evolution is far more surprising. These gravitational behemoths don't just take, they regulate, shaping their galaxies with bursts of energy that act like a cosmic thermostat. When a black hole feasts on surrounding gas, it doesn't digest quietly. Instead, it belches out colossal jets of radiation and plasma, heating interstellar gas to millions of degrees. This violent output might sound destructive, but it's actually a lifesaver for galaxies, preventing them from burning through their fuel too fast. Picture a galaxy where star formation runs unchecked. Gas clouds collapse in a frenzy, spawning stars so rapidly they exhaust the galaxy's reserves in a cosmic blink. Without something to temper this process, galaxies would flame out early, leaving behind barren wastelands of aging stars. That's where black hole feedback steps in. The energy from these outbursts keeps gas too hot to collapse, putting star formation on pause until conditions stabilize. It's like a chef adjusting the heat under a simmering pot, ensuring the meal cooks evenly rather than boiling over. The galaxy cluster MS0735 offers a stunning example. Its central black hole pumps out enough energy to heat the surrounding gas to nearly 50 million degrees, creating a vast bubble where star formation is effectively put on hold. But the story doesn't end there. These outbursts don't just suppress star formation, they sculpt galaxies on monumental scales. The jets carve out cavities in intergalactic gas, shaping the very architecture of galaxy clusters. In some cases, the displaced gas eventually cools and falls back toward the galaxy in a cosmic rain, reigniting star formation in controlled bursts. The Perseus cluster showcases this beautifully. Its black hole's jets have created ripples in the hot gas, like sound waves in air, which may eventually trigger new stellar nurseries at precise distances from the center. This delicate balance between heating and cooling ensures galaxies don't just thrive but evolve, their growth paced over billions of years rather than squandered in a short-lived blaze. What's truly remarkable is how finely tuned this system appears. Observations suggest that supermassive black holes regulate their own feeding. The more gas they consume, the more energy they release, which in turn blows away nearby gas and starves the black hole until the cycle begins anew. This self-correcting mechanism keeps galaxies in equilibrium. Their star formation rates neither too high nor too low. Without it, the universe might lack the stable environments needed for planets and life to emerge. So while black holes may rule through gravity, their greatest power lies in their ability to give back, transforming chaos into cosmic order one outburst at a time. Galactic winds howl through the cosmos like invisible hurricanes, carrying the breath of dying stars across unimaginable distances. These aren't gentle breezes, they're supersonic rivers of gas, charged particles, and heavy elements, blasted outward at speeds exceeding thousands of kilometers per second. When a cluster of massive stars explodes as supernova, or when a supermassive black hole awakens and spews jets of energy, the resulting shock waves can lift entire oceans of gas clear out of a galaxy's grasp. At first glance, this seems catastrophic, a cosmic hemorrhage stripping galaxies of their star-forming fuel. But look closer, and you'll discover nature's grand recycling scheme in action. Take the starburst galaxy Messier 82, a celestial fireworks display 12 million light-years away. Here, stars are born so furiously that their combined radiation and supernova explosions have created a bipolar wind, a titanic outflow shooting perpendicular to the galaxy's disk. This wind carries enough material to build millions of suns, hurling it hundreds of thousands of light-years into intergalactic space. But here's the twist: that expelled gas isn't lost forever. As it travels, it mixes with pristine hydrogen from the cosmic web, cooling over millions of years until gravity begins pulling it back, not necessarily to its home galaxy, but perhaps to a neighboring one. The universe, it seems, prefers shared resources. Black hole-driven winds take this process to even greater extremes. In galaxies like Markarian 231, the central supermassive black hole doesn't just eat, it dines with such ferocity that it powers quasars, whose radiation pressure can push gas outward at relativistic speeds. These winds create vast bubbles in the intergalactic medium, like ripples from a stone tossed into a pond. Yet within these bubbles, magic happens. The leading edges compress surrounding gas, triggering collapses that birth new stars far from their galactic origins. It's a cosmic relay race. One galaxy's loss becomes another's gain, with black holes acting as unwitting middlemen. The most stunning evidence of this cycle lies in the circumgalactic medium, the gauzy halo of gas surrounding galaxies. Observations from instruments like the Hubble Space Telescope reveal these halos are brimming with heavy elements: carbon, oxygen, iron, the building blocks of planets and life. These elements shouldn't be there unless they were carried outward by galactic winds, proving that what goes up must eventually come down. Over billions of years, this enriched material rains back onto galaxies in a process astronomers call galactic fountain effects, seeding future generations of stars with the ashes of their ancestors. Far from being destructive, these winds are the universe's way of stirring the pot. Without them, galaxies would quickly exhaust their gas, burning out in a blaze of short-lived stars. Heavy elements would remain locked in galactic cores, never enriching the cosmos at large. The winds ensure a balanced ecosystem, one where materials circulate freely, where no galaxy is an island, and where every ending sows the seeds of new beginnings. So the next time you hear of a galaxy losing its gas, remember, it's not vanishing. It's just taking a cosmic detour before returning, transformed, to fuel the next chapter in an endless story of renewal. Dark energy is the universe's silent game changer, an invisible force working on scales so vast it makes galaxies seem small. Unlike gravity, which pulls matter together, dark energy pushes space itself apart, accelerating the expansion of the cosmos at an ever-increasing rate. Right now, its effects are subtle. Galaxies in our local group still cling together, and collisions like the impending Milky Way Andromeda merger will still occur. But zoom out to cosmic timescales, and dark energy's influence becomes undeniable. Over trillions of years, as the space between galaxy clusters stretches exponentially, even the closest neighbors will fade from view, receding faster than light can bridge the gap. This isolation poses a profound challenge to the cycle of galactic rebirth. Without fresh mergers or infalling gas from the cosmic web, galaxies will exhaust their star-forming fuel, their stellar populations aging into red dwarfs and white dwarfs. The vibrant dance of destruction and renewal we see today, supernova enriching gas clouds, collisions triggering starbursts, will slow to a crawl. Yet dark energy doesn't mean stagnation. Local processes will still shape galaxies, just on longer timelines. Supermassive black holes will continue their quiet regulation, their occasional outbursts preventing remaining gas from collapsing too quickly. Isolated dwarf galaxies might still merge with their hosts, offering pockets of rejuvenation. And in the densest regions of galaxy clusters, where gravity temporarily overcomes dark energy's pull, some last vestiges of interaction could persist. The most fascinating twist, dark energy's dominance might reveal new modes of galactic evolution. In distant futures, as galaxies grow ever more solitary, their internal dynamics could become the primary driver of change. Tidal interactions between stars, the gradual evaporation of globular clusters, and even the slow decay of black holes through Hawking radiation will take center stage. Galaxies won't die, they'll enter a kind of cosmic retirement, their stories continuing in whispers rather than roars. Even in this lonely era, the universe will find ways to innovate. Some theorists speculate that quantum fluctuations in the vacuum of space, the same phenomenon driving dark energy, might eventually spawn new particles or energy states, offering unforeseen pathways for renewal. While dark energy stretches the cosmic tapestry thin, it can't erase the underlying creativity of physical laws. The cycle may slow, but it won't break, proving once again that the universe's greatest constant isn't stasis, but adaptation. The universe may appear timeless when we gaze at the night sky, but its vibrant cycles of destruction and rebirth are actually on borrowed time. As the cosmos expands and dark energy accelerates its growth, the grand ballet of galactic collisions and stellar fireworks will gradually slow to a whisper. Star formation rates peaked around 10 billion years ago, and they've been declining ever since. Today, the universe produces only about half as many stars as it did at its peak. Yet this isn't a simple march toward darkness, it's a transition into a new phase of cosmic evolution, one where the rules of renewal change but never disappear. Consider the fate of spiral galaxies like our Milky Way. Their iconic arms, currently brimming with blue-white young stars and pink stellar nurseries, will gradually lose their luster. As gas supplies dwindle, fewer stars will ignite, leaving aging red giants and white dwarfs to dominate the stellar population. The brilliant blue arms will fade to dull red, and the spiral structure itself may blur as random stellar motions erase its once sharp definition. But even in this twilight, creation persists. The occasional collision between brown dwarfs, failed stars too small to sustain nuclear fusion, could trigger late-stage stellar births, creating faint red dwarfs that will burn for trillions of years. Elliptical galaxies, already dominated by older stars, face a different trajectory. Having exhausted most of their gas in past bursts of star formation, they'll grow even redder and dimmer. Yet here, too, surprises lurk. Tidal interactions between stars can occasionally strip gas from aging red giants, creating small reservoirs of fresh material. In the densest galactic cores, this recycled gas might still collapse into new stars, not the brilliant blue giants of youth, but modest stellar embers that glow faintly for eons. The most enduring light will come from the smallest stars. Red dwarfs, barely 1/10 the sun's mass, burn their fuel so slowly they can shine for 10 trillion years, far longer than the current age of the universe. These faint, ruby-colored stars will become the torches of the far future, their steady glow outlasting all other stellar types. Around them, planets may still harbor life, their surfaces warmed not by youthful suns but by these ancient, patient embers. Black holes, too, will play a final act in this cosmic drama. As galaxies grow darker, their supermassive black holes will continue merging, releasing gravitational waves that ripple through spacetime. Over incomprehensible timescales, even these titans will evaporate through Hawking radiation, but not before funneling the last wisps of galactic gas into faint accretion disks, their dying glow a final testament to the universe's creative potential. What emerges from this far future landscape isn't an end, but a transformation. The cycles won't stop, they'll simply unfold on scales we can barely imagine. Stellar collisions will still occur, just less frequently. Gas clouds will still collapse, just more slowly. And when the last stars finally wink out, quantum processes we're only beginning to understand may yet spark new forms of cosmic rebirth. The universe doesn't do finales, only transitions, each one paving the way for the next act in an epic without end. Could galactic rebirth continue forever, or does the universe have an expiration date? At first glance, the cosmic cycle of destruction and renewal seems unstoppable. Stars explode, galaxies merge, and new structures emerge from the ashes. But hidden beneath this vibrant dance lies an unavoidable truth. Entropy, the slow but steady unraveling of order into chaos, is the universe's ultimate clock. Right now, the cosmos is still rich with fuel for rebirth. Giant molecular clouds drift between stars, galaxies collide in spectacular mergers, and black holes churn the interstellar medium like cosmic mixers. But these processes aren't infinite. Every supernova that enriches space with heavy elements also scatters energy that can never be fully reclaimed. Every galactic collision, while breathtaking, converts some usable gas into forms too diffuse for future stars. Even dark energy's accelerating expansion stretches the cosmic web ever thinner, making it harder for galaxies to access fresh material. The numbers tell a sobering story. Based on current star formation rates, the universe has already used up about half its available gas. In about 100 trillion years, the last conventional stars will flicker out, leaving only fading white dwarfs and cooling neutron stars. Without new stellar generations, the cycle of galactic rebirth will slow to a crawl. Yet even in this distant era, flickers of renewal may persist. Brown dwarfs, failed stars too small to ignite fusion, could still collide, triggering delayed stellar births. Black holes might siphon the last wisps of gas from interstellar space, their accretion disks glowing faintly like cosmic embers. But here's the twist. The universe has surprises up its sleeve. Quantum fluctuations in the vacuum of space could theoretically spawn new particles over incomprehensible timescales, offering trace amounts of fresh material. Some theories even suggest that proton decay, if it occurs, would release energy that might over quadrillions of years feed new structures, and in the absolute far future, hawking radiation from evaporating black holes could become the universe's final energy source, a whisper of activity in an otherwise silent cosmos. So while the era of grand galactic rebirth won't last forever, it's far from over. For trillions of years to come, the universe will keep finding ways to reinvent itself, even if on smaller scales. The cycles we see today, violent, brilliant, and awe-inspiring, are just the opening act of a story so long we can barely comprehend it. And that's the most humbling realization of all. On cosmic timescales, even entropy moves slowly enough to leave room for wonder. Every atom in your body holds a cosmic secret, a story written in the fires of long-dead stars. The calcium in your bones, the iron in your blood, even the gold in your jewelry were forged in stellar furnaces billions of years ago, then scattered across the galaxy by supernova explosions. We aren't just observers of the universe's grand cycles, we're living proof of their creative power. When you breathe, you're inhaling oxygen atoms that once floated in interstellar clouds. When you gaze at the stars, you're looking at distant relatives in a family tree woven from stardust and gravity. This connection runs deeper than chemistry. The very rhythm of our existence mirrors the universe's heartbeat. Just as galaxies experience periods of furious star birth followed by quiet maturity, human life unfolds in cycles of growth and renewal. Our planet's seasons echo the cosmic dance of destruction and rebirth, winter's dormancy giving way to spring's explosion of life, much like the quiet between stellar generations before new stars ignite. Even our cells replace themselves over time, with most of your body's atoms being swapped out every 7 years, a personal microcosm of cosmic recycling. By studying these grand universal processes, we're essentially reading our own origin story. The James Webb Space Telescope doesn't just show us distant galaxies, it reveals the nursery conditions that made our solar system possible. When astronomers analyze the chemical composition of ancient stars, they're piecing together the recipe that led to planets, oceans, and eventually, life. The carbon essential to DNA, the nitrogen in our atmosphere, even the uranium that heats Earth's core, all were forged in stellar deaths that occurred before our sun even existed. Perhaps most humbling is the timescale. The hydrogen atoms in your body's water molecules are nearly as old as the universe itself, formed in the first minutes after the Big Bang. They've survived supernova-ridden galactic winds and traveled billions of light years before becoming part of you. In this way, every human is a walking archive of cosmic history, carrying fragments of stars that died when the Milky Way was young. This perspective transforms how we see our place in the universe. We're not separate from the cosmos, we're its most curious offspring, the universe's way of understanding itself. When a child marvels at the night sky, that's stardust contemplating stardust. When a scientist deciphers the laws of physics, that's the universe becoming self-aware. Far from being insignificant in the vastness of space, we're proof that galactic rebirth isn't just about stars and gas. It's a process that, against unimaginable odds, led to conscious beings who can trace their lineage back to the first moments of time. The search for life beyond our solar system leads us to an astonishing realization: every ingredient needed for biology exists because stars lived and died. Picture a planet orbiting a distant sun, its oceans rich with organic molecules, its atmosphere brimming with oxygen. None of this would be possible without the violent deaths of earlier stellar generations. When massive stars explode as supernova, they don't just vanish, they scatter carbon, nitrogen, and oxygen across light years of space. These elements, forged under extreme pressures and temperatures, become the building blocks for new solar systems and potentially new life forms. Consider the case of phosphorus, a crucial element for DNA and cell membranes. Unlike lighter elements that form readily in stars, phosphorus requires especially energetic conditions to create. Recent studies suggest most of Earth's phosphorus came from a specific type of supernova explosion, meaning our very genetic code might trace back to a particular stellar death billions of years ago. Now imagine this process repeated across billions of galaxies, each one cycling heavy elements through generations of stars and planets. The raw materials for life aren't rare cosmic accidents, they're inevitable byproducts of galactic evolution. The timing of these cycles matters just as much as the materials themselves. Too early in a galaxy's history, and there wouldn't be enough heavy elements for rocky planets. Too late, and the star formation rate might drop too low to sustain planetary systems with stable climates. Astronomers call this the galactic habitable zone, the sweet spot in space and time where conditions align for life to emerge. Our Milky Way reached this zone about 5 billion years ago, when enough supernova had enriched the interstellar medium, but before stellar births became too infrequent. Other spiral galaxies likely follow similar patterns, their habitable zones expanding outward from the core over time like ripples in a pond. But what about extreme environments? Some of the most intriguing possibilities lie in galaxies undergoing intense starbursts, where star formation rates skyrocket due to collisions or gas inflows. While these chaotic regions seem inhospitable, they might actually accelerate the production of life-friendly elements. The dwarf galaxy Zwicky 18, for example, formed most of its stars only recently in cosmic terms, yet already shows signs of heavy element enrichment. Planets forming in such systems would have access to a rich chemical palette from their very beginning, possibly giving life a head start, provided they can survive the frequent supernova and intense radiation of their stellar nurseries. The greatest cosmic irony might be this: the same destructive forces that make space seem hostile, supernova, gamma-ray bursts, even galactic collisions, are the very mechanisms that create and distribute life's essential ingredients. Without stellar explosions, planets would lack the minerals for tectonic activity. Without galactic mergers, fresh gas supplies might run dry, leaving star systems without the resources to sustain biospheres over billions of years. The universe doesn't favor life, but it creates the conditions where life can emerge as part of its natural cycles. Every time we discover another exoplanet with water or organic molecules, we're seeing galactic recycling at work, proof that the story of life is inseparable from the story of cosmic destruction and rebirth. Imagine a structure so vast it encircles an entire star, harnessing its energy on a scale that defies comprehension. This isn't science fiction, it's a Dyson sphere, one of many potential technosignatures that could reveal advanced civilizations scattered across the galaxy. The concept comes from physicist Freeman Dyson, who theorized that sufficiently advanced societies might build megastructures to capture stellar energy, leaving detectable traces in infrared light as excess heat radiates into space. Astronomers have already scanned thousands of stars for such anomalies, finding intriguing candidates like Tabby's star, whose irregular dimming patterns sparked years of speculation about alien megastructures before dust clouds were confirmed as the likely culprit. But Dyson's spheres are just the beginning. Technosignatures could take forms we've barely imagined: planets with atmospheric chemicals like CFCs indicating industrial activity, laser pulses deliberately sent as cosmic hellos, or even waste heat from sprawling interstellar civilizations. The Breakthrough Listen project scans millions of radio frequencies nightly, listening for engineered signals amid the cosmic noise. Meanwhile, the James Webb Space Telescope's ability to analyze exoplanet atmospheres brings us closer than ever to detecting chemical fingerprints of technology, like nitrogen dioxide from combustion or artificial greenhouse gases stabilizing alien climates. The most haunting possibility: these signatures might not come from living civilizations at all. If intelligent life tends to rise and fall within galactic cycles, expanding during eras of cosmic calm, then vanishing in catastrophes or transcending to forms we can't perceive, we might only ever find their ruins. Imagine stumbling upon a dead stellar engine still orbiting a white dwarf, or an ancient beacon transmitting into the void long after its builders are gone. The universe has had billions of years to host civilizations before ours. Their artifacts could be hidden in plain sight, disguised as natural phenomena or buried in datasets waiting for the right algorithm to uncover them. This search does more than satisfy curiosity. It forces us to confront humanity's own trajectory. Every Dyson sphere candidate is a mirror showing our possible future, every silent exoplanet a cautionary tale. If civilizations commonly destroy themselves upon reaching technological maturity, the cosmic silence makes tragic sense. But if some learn to endure across galactic timescales, their survival strategies could become our roadmap. The Great Filter, whether it's behind us or ahead, looms large in this quest. Ultimately, hunting for technosignatures reshapes how we see our place in the cosmos. Whether we find neighbors, ghosts, or solitude, the answer will rewrite humanity's story. And perhaps in studying how other civilizations might have risen or fallen with their galaxy's rhythms, we'll discover how to synchronize our own survival with the universe's grand tempo. The silence of the cosmos is one of its greatest mysteries. With billions of galaxies, each containing billions of stars, the universe seems like it should be teeming with civilizations. Yet, as physicist Enrico Fermi famously asked, "Where is everybody?" this paradox becomes even more haunting when we consider galactic rebirth cycles. If destruction and renewal are woven into the fabric of the cosmos, could these very processes be the reason we find ourselves seemingly alone? Imagine a civilization reaching its technological peak just as its host galaxy undergoes a catastrophic merger. The gravitational chaos could disrupt planetary orbits, flinging worlds into deep space or plunging them into their sun. Nearby supernova, triggered by the collision's shockwaves, might bathe entire star systems in lethal radiation. Even without direct impacts, the sudden influx of energy from a newly awakened supermassive black hole could sterilize whole regions of a galaxy in an instant. These aren't hypotheticals. We've observed galaxies like the Cartwheel Galaxy, where a collision has triggered a shockwave of star formation and destruction, rippling outward like a stone dropped in a pond. Any civilizations caught in those waves would face existential threats beyond anything Earth has endured. But galactic cataclysms aren't the only reset buttons. Consider the quiet killers, slow cosmic droughts. As galaxies age and star formation slows, the availability of heavy elements crucial for technology, like uranium for nuclear power or rare earth metals for electronics, could dwindle. Civilizations might rise only to find their growth stunted by a lack of resources, their progress capped by the very cycles that once enriched their worlds. The Dwarf Galaxy Segway 1 offers a glimpse of this fate, a system so ancient and chemically depleted that it's essentially a fossil, its star-forming days long past. There's another, darker possibility. What if advanced civilizations inadvertently trigger their own demise during galactic upheavals? A society facing an imminent gamma-ray burst might desperately build protective megastructures, only to destabilize their star in the process. Or consider a civilization that harnesses black hole energy only to miscalculate and ignite a feedback loop of destructive energy. The same ingenuity that lifts a species to greatness could become its downfall during times of cosmic turbulence. Yet amid these grim scenarios, a subtle hope emerges. If civilizations rise and fall with galactic cycles, then their legacies might still linger, not as radio signals or Dyson spheres, but as chemical fingerprints in starlight. Future telescopes could detect industrial pollutants in exoplanet atmospheres, even if the polluters are long gone. The ruins of megastructures might orbit dead stars waiting to be discovered. And if some civilizations do survive these resets, they've likely mastered synchronization with their galaxy's rhythm, building not just for their era, but for the next cosmic cycle. The Fermi paradox might not be a paradox at all, but a reflection of the universe's relentless cadence. Civilizations could be like fireflies in a storm, flaring brightly for a moment before the wind extinguishes them, only for new lights to spark when conditions allow. If that's true, then our search for others isn't just about finding neighbors, it's about learning how to outlast the storm. Humanity stands at a crossroads unlike any in our history. Do we remain tethered to Earth or embrace our destiny among the stars? The universe doesn't offer permanence. Entire galaxies rise and fall in cycles spanning billions of years. If our species hopes to endure beyond the lifespan of a single planet, we must learn to surf these cosmic waves rather than fight them. The same forces that tear galaxies apart also create opportunities. Supernova enrich the cosmos with life-giving elements. Colliding galaxies ignite stellar nurseries, and even black holes sculpt the conditions for rebirth. Our survival may hinge on recognizing these patterns and adapting to them. Consider the lessons from galactic evolution. When galaxies merge, their stars rarely collide. Space is too vast, but their gas clouds compress, triggering new star formation. This suggests a strategy. Instead of fearing cosmic upheaval, advanced civilizations could position themselves in regions where chaos breeds creation. Imagine fleets of generation ships riding the gravitational tides toward colliding galaxies, arriving just as fresh resources become abundant, or habitats designed to harvest the heavy elements spewed by supernova, turning destruction into construction materials. The universe's greatest recyclers, stars, operate on timescales we can't yet match, but their principles could guide our expansion. Timing is everything. Right now, the Milky Way is relatively calm, but in 4 billion years, our collision with Andromeda will unleash a firestorm of star birth. A civilization planning for the long term wouldn't just survive that event, it would thrive by preparing. Orbiting young stars born from the merger, mining metals from newly formed asteroids, or even harnessing the energy of freshly awakened black holes. The difference between extinction and eternity might come down to anticipating these cycles rather than reacting to them. Yet interstellar travel isn't just about escaping doom, it's about seizing cosmic opportunities. The same galactic winds that strip gas from galaxies also distribute enriched materials across intergalactic space. A species adept at riding these currents could colonize not just stars, but entire galaxy clusters, using the universe's own dynamics as propulsion. Picture megastructures floating in the halos of galaxies, drawing energy from infalling gas, or settlements around red dwarf stars so stable they'll outlive the Milky Way itself. The ultimate lesson from Galactic Rebirth is this: stagnation is the real threat. Civilizations that cling too tightly to one world, one star, or even one galaxy risk becoming fossils in an ever-changing cosmos. But those who embrace the universe's rhythm, its cycles of destruction and renewal, might find themselves not just surviving, but evolving into something far greater. Our future isn't written in stardust yet, but the blueprint is there, hidden in the dance of colliding galaxies and the glow of newborn stars. All we have to do is learn to read it. Humanity stands on the brink of becoming more than just observers of cosmic cycles. We're preparing to become active participants. This shift brings profound ethical questions. Take asteroid mining, for example. These floating mountains of metal and ice aren't just resources, they're time capsules from the solar system's formation, containing clues about how planets like Earth came to be. If we mine them without care, we might erase scientific treasures while disrupting delicate orbital balances that have existed for billions of years. The same metals that could build our space habitats are also the building blocks for future cosmic processes: iron that might one day form new planets, or water ice that could seed life elsewhere. But the dilemma runs deeper than preservation versus progress. Consider stellar energy harvesting, the dream of capturing a star's full output with Dyson swarms or similar megastructures. While this could power civilizations for eons, it might also alter a star's life cycle in unexpected ways. Stars aren't isolated power plants, their solar winds and radiation pressures shape entire planetary systems and nearby interstellar clouds. Divert too much energy, and we might unintentionally change the temperature gradients that make some regions habitable while rendering others barren. It's like removing a single thread from a tapestry. The entire pattern might unravel in ways we can't predict. The ethical framework we need doesn't exist yet. On Earth, we debate conservation versus development within ecosystems we understand. In space, we're dealing with systems orders of magnitude more complex, where our actions could have consequences lasting billions of years. Some argue for the prime directive approach, observing without interfering in natural cosmic processes. Others point out that change is the universe's constant. Galaxies collide, stars explode, and planetary systems form from destruction. Why should human activity be any different? Perhaps the answer lies in finding balance, mining asteroids but leaving some pristine for scientific study, or developing stellar energy systems that work with a star's natural rhythms rather than against them. The upcoming era of space telescopes like the Habitable Worlds Observatory could help by identifying solar systems where our interventions might do the least harm. And as we learn to read galactic cycles more accurately, we might discover optimal windows for resource use, times when extraction would have minimal impact on ongoing cosmic processes. This isn't just about avoiding harm, it's about recognizing our potential role as cosmic gardeners. Just as black holes regulate galaxy growth and supernova enrich star-forming regions, advanced civilizations might one day help steer these processes toward outcomes that benefit both nature and intelligence. The choices we make in the coming centuries will determine whether humanity becomes a destructive force or a constructive participant in the universe's grand story of renewal. Either way, one thing is certain: we're about to graduate from being products of cosmic evolution to becoming shapers of it. The universe writes its story in stardust and fire, a never-ending epic where every ending is secretly a beginning in disguise. When we look up at the night sky, we're not just seeing distant stars, we're witnessing chapters in a cosmic saga that's been unfolding for 13.8 billion years. Those brilliant pinpricks of light, they're the offspring of ancient supernova. The faint glow of nebulae, they're celestial nurseries where tomorrow's stars are already taking shape. Even the void between galaxies isn't truly empty, it's a reservoir of potential, holding the raw materials for futures we can barely imagine. Consider the humble carbon atom in your fingertip right now. It might have formed in the heart of a red giant star that died before our solar system was born, been flung across space by a supernova shockwave, then drifted for eons until it became part of a molecular cloud that birthed our sun. That same atom could one day be recycled again, perhaps when our dying sun expels its outer layers, returning enriched material to the galaxy for new stars and planets. This isn't poetry, it's the hard physics of cosmic renewal, written in the language of stellar nucleosynthesis and galactic dynamics. What's truly humbling is realizing how deeply we're woven into this story. The calcium in your bones, the iron in your blood, these aren't just biological necessities, they're cosmic souvenirs. Every breath you take contains oxygen atoms forged in multiple generations of stars, mixed and remixed across billions of years. When astronomers study distant galaxies, they're not just mapping the universe, they're tracing our elemental lineage, that spiral galaxy a million light-years away. Its future collisions will create elements that might one day become part of beings not so different from us. Yet for all we've learned, the greatest revelation might be how much remains unknown. Dark matter's gravitational grip shapes galactic evolution, but we still don't know what it is. Dark energy accelerates the universe's expansion, yet its nature eludes us. Even the fate of galaxies, whether they'll slowly fade or be reborn in some future cycle, holds mysteries that push the limits of our understanding. This isn't discouragement, it's an invitation. Every unanswered question is a doorway to new discoveries, a reminder that the universe always has more stories to tell. So keep looking up with wonder, but also with purpose. The same forces that shaped galaxies are at work in you right now. The gravity that binds stars together also flows through your veins as the electromagnetic force animating your neurons. We are, in the truest sense, the universe becoming aware of itself. And as we continue exploring with telescopes, with spacecraft, with the limitless curiosity that defines our species, we're not just observers of cosmic rebirth. We're living proof of its most astonishing possibility, that stardust can contemplate stars and chaos can give rise to meaning. The story isn't finished. In fact, it might be just beginning.